In that case, output will be 1. Or if A is 0, B is 1, output again will be 1. And when both are 1, output again is 0. So what is important here is that either both A and B are 0, or when both A and B are 1, output is 0. And when either of the one is 1 and other is 0, the output is 1. So that's the truth table for exclusive OR gate. This is somewhat similar to what you have done for OR gate, but there, this, when both were 1, output was 1. So that is why exclusive OR gate. I mean, whenever any two, whenever both of the inputs are exactly the same, either 0 or 1, the output is 0. So that is called exclusive OR gate. This can also be described as something like, okay, A or B, but not both, gives output 1. So this is the symbol for exclusive OR gate. I mean, you have an OR gate, and then there is additional curve like this here. So this is representing a 2-input exclusive OR gate. So then what should be the Boolean expression for exclusive OR gate? I mean, okay, this is the symbol, Boolean symbol you can say, and this is the full Boolean expression for exclusive OR operation. So how we can describe this in terms of a Boolean expression? So we can write down this A B bar or A bar B. So now if you follow this expression, you will be seeing that this produces the whole table. Let us try to take some example. I mean, suppose when A is 0, B is 0. Both A and B are 0. So what will be this part? A is 0, so this is 0, and B bar. B bar will be 1. But then 0 and anything will be 0. Similarly here, A bar will be 1, but B is 0. So this expression will also give you 0. So 0 or 0 will be 0. Correct? Let's take another example. I mean, another set of inputs. Say B is 0, A is 1. So whenever B is 0, B bar will be 1. So A is 1, 1, and what is B bar? 1. 1 and 1 will be 1. And what will be this? A bar will be 0. B is already 0, so 0. So 1 or 0 will be 1. Similarly, you can find out for this combination of inputs. This will again give you 1. What about this one then? Now try to see. B is 1, A is also 1. So what is B bar? B bar is 0. So 1 and B bar, which is 0, will be 0. Or A bar, which is again 0, and B, which is 1. So 0 or 0 will be 0. So that's the expression which can describe this exclusive OR gate. Now, question is, okay, how to realize this with the help of those fundamental gates or basic digital gates which we have studied. This is just a full. This is representing exclusive OR operation. Now the question is, how is this expression or this gate related to the fundamental building blocks? Like okay, one set of gates is AND, OR, and NOT gate. If you use those 3 gates, you can design any Boolean expression or any digital circuit, any truth table. And other option may be like, okay, using only NAND gates or NOR gates. That's another way. Right, so let us try to first understand exclusive OR operation with the help of AND, OR, and NOT gate. So this is the circuit which is showing implementation of exclusive OR expression with the help of AND, OR, and NOT gates. So you can see, okay, this expression, this is a AND gate. So what is the input to this? A directly going to this, and B NOT. This is B bar. So B bar means NOT operation of B. So this is going here. So here input is A, here is B bar. So what will be the output? A and B bar. Similarly here to this AND gate, B is going directly, A is going as A bar after this NOT gate. So what will be the output of this AND gate? A bar B. So we have to OR both so that we can obtain this expression. So what will be the output of this OR gate? A B bar or A bar B, which is nothing but exclusive OR gate. Exclusive OR gate can also be obtained with the help of those NOR gates. You know, we have studied that NOR gates are also the basic building blocks, or they are universal gates. So we can use even NOR gates to obtain exclusive OR gate. So here you can see this is these two circuits are equivalent as such. If you see, because these are the NOT gates here, because exclusive OR gates being used as NOT gates. And then this is being fed to NOR gate. Now you will say, okay, we are not using AND gate here. But then you will see that this NOR gate with NOT gates at input will be equivalent to AND gates. We will be doing this in Boolean algebra part. There are certain theorems which we will be using and proving as well. So this, so that we can establish the equivalence of these two circuits. If you are not convinced, you can try that simple hit and trial table, truth table actually. Okay, let us say, okay, if A is 1, sorry, if A is 0, B is 0, you can try to see what will be the output. So if A is 0, what will be the output here? It is going to be 1 because it is a NOT gate, correct? So it will be 1 here. Similarly, B 0, again 1 here, both inputs 1. So what will be the output here? It will be, what will be the output here when both inputs are 1? What will be the output at this point? Yes, waiting for your response. It will be 0, correct, because this is a NOR gate, correct? So this is 0, and here we were saying, okay, both A and B are 0. When both A and B are 0, then again what will be the output here? 1, isn't it? So one input here is 0, other input here is 1. So what will be the output at Q? What will be the output at Q? No, that's not 1, Pranjal. This will be 0. You cross check your table and do it quite carefully. Well, so that proves the first row of your truth table. That is, when both A and B are 0, output is 0. Then you can try with B0, A1. This circuit is the one which we are following. So B0 means what will be the output here? That is 1. And A is 1. So A is 1 means output here is 0. So here what is input? 1. Here is 0. So then what will be the output here? 0, isn't it? Output at this point will be 0 if I'm not wrong. Well, then if you take what was B, B was 0 and A was 1. So B0 means and A1 means output here is 0 once again, because B is 0, A is 1. So 1 means this is NOR gate. So output will be again here 0. So both will be 0, 0. What will be the output here? 1. So Q will be 1. I'm sure you are not uncomfortable with this. What these guys are doing, Parikshit and all, they are joining so late. Fine. So this is how you can prove for other combinations of input from this table. This is how you can check a particular circuit. So you have to try it by taking different combinations of inputs and then see if your circuit is working proper way or not. This is another implementation of exclusive OR gate. So there can be different ways of getting exclusive OR gate. Now this implementation is with the help of NAND gates. Again, one way to do this is to verify with the help of the truth table. But I won't be doing that for you. You can draw this circuit and do it yourself. And there is another easier way of doing this, somewhat easier, I would say, and that is with the help of expressions of Boolean algebra. So that I will be pointing out in the next class, that how we can prove that, okay, what will be the output here. And coming lectures are going to contain all these things in detail. Well, then there is a question that what is the need for exclusive OR gate, or why is it so important that we separately wanted to discuss this? So basically, I hope you remember that table for addition of binary numbers. So if we have two 1-bit binary numbers, what will be the sum? Something like, okay, you have 0, you have 0, what will be the output? Sum of 0 plus 0 is 0, 0 plus 1 will be 1, 1 plus 0 will again be 1, 1 plus 1 will be 1, 0, but we are dealing with 1-bit system. So that will be 0. Carry has to be discarded, because if we are dealing with 1-bit system only, then output will be 0 here. And this table is similar or exactly same as that of the truth table of exclusive OR gate. And that is where lies the significance of exclusive OR gate. So basically, exclusive OR gates can be used for performing operation of binary addition. So here we have seen only single 1-bit binary adder, which is directly nothing but an exclusive OR gate. Then we will be doing it in coming classes again, that how we can design multi-bit binary adder with the help of exclusive OR gates. So this very important result highlights the significance of exclusive OR gates. Means as a binary adder they are used. There are other applications as well. We will be coming to that as well. There is something called parity generator, parity checkers, which are very crucial components of communication systems. So that is coming in our coming slides. Well, that was our 2-input exclusive OR gate. Now we will be talking about 3-input exclusive OR gate. So 3-input exclusive OR gate, the symbol looks like this. How we write down that in the form of Boolean expression, it is like this. This plus and circle around it represents exclusive OR operation. So a 3-input exclusive OR Boolean expression looks like this. And how is the truth table? Now you try to count the truth table. Let us try to understand the truth table in little more detail. Because in case of 2-input, it was very simple. Now, how will that exclusive OR operation be performed in 3-input case? So suppose we have 3 inputs, A, B, C, right? So if all 3 are 0, output is 0. If any one of the 3 is 1, then output will be 1. Now you can notice here A is 1, the output is 1. Here only B is 1, output is 1. Here A and B both are 1, but then output is 0. I'm saying if any one of either A or B or C are 1, then output will be 1. Same here only C is 1, so output is 1. All other cases, output is 0, except for this case, when all A, B, C are 1. So basically, what is exclusive OR operation is that if we have odd number of inputs being 1, then output will be 1. And if there will be even number of inputs being 1, output will be 0. That's what represents the exclusive OR operation. Is that clear, or any question from this part? Okay. Any other student having any query or doubt or confusion? No. Well, so now what should be the detailed Boolean expression for this? This is how we can represent the Boolean expression for three input exclusive OR gate. So you can now verify with the help of this expression that this truth table comes out to be true. You can do it at your own. I mean, suppose we try all A, B, C are 0, then I mean, all A, B, and C are 0. So whatever B bars, B, C whole bar, this is being multiplied by A, which is 0. So it is not multiplication as such, it is uh, AND with BC. So in AND gate, if any one of the input is 0, output will be 0. Correct? Same is the case here. Same is the case with this term and this also. I mean, all three terms are 0, of course, so output will be 0. So if you OR all the zeros, output will be again 0. So that's what represents the first row, or how we can explain. Then you can try for second, third, and so on. So this expression describes the three input exclusive OR gate. Well, then how we can design a three input exclusive OR gate? Well, two input exclusive OR gate we have seen in the previous slides, like here, how we can design two input exclusive OR gate. Now, once you have two input exclusive OR gate, from this you can design three input exclusive OR gate by using this expression. So you have this one as a two input exclusive OR gate. If you feed its output to this another exclusive OR gate and keep this one as the input for third bit, then this operation will be nothing but representing our three input exclusive OR operation. You can verify that. And what is the symbol for three input exclusive OR gate? This is the symbol for that. So this is similar to exclusive OR gate with three input lines. Similarly, if you have three input exclusive OR gate, then you can also design four input exclusive OR gate. You have to put another exclusive OR gate here, and three inputs are already here. One of that exclusive OR gate input goes here. So all these four combined represents a exclusive OR gate. Similarly, this represents a six input exclusive OR gate. 1, 2, 3, 4, 5, 6. How these are connected, notice this. And then you can realize that how we can design any. So this part up to here is representing four input exclusive OR gate. And then you use another one and then put in this exclusive OR gate. This full circuit represents six input exclusive OR gate, which we can represent in this way. So this is how we can realize any number of input exclusive OR gate, or this is how we can realize exclusive OR gate with n number of inputs. Is this part clear? Is this part okay? Well, next type of gate is exclusive NOR gate. Now, as we have exclusive OR gate, as the name indicates here, XNOR gate means it is nothing but exclusive OR gate appended with NOT gate. So this represents exclusive NOR operation. And here is the Boolean expression for this. I mean A exclusive B whole bar. So this is representing exclusive NOR gate. And what should be the truth table for exclusive NOR gate? You can see from here. I mean, whenever both A and B are 0, output is 1, which is just complement of exclusive OR gate. And when in second case again, when both are 1, output is 1. And when either of the two is 1, output is 0. So this represents exclusive NOR operation. How we can realize exclusive NOR operation? Now you can see this circuit. Again, there are various ways of proving this, but we can note it for time being as such. Then when we will be discussing those Boolean algebra theorems, I will be talking about this in details. So here you have A and B as inputs. They are being inverted, I mean not operation. And then to this AND gate goes A bar, B bar, because they have been inverted. So this A bar, B bar represents the output of this gate. And similarly, this is showing A, B. And when these two are fed into inputs of OR gate, then the expression here becomes A bar, B bar, or AB, which is also this one, A exclusive B bar, or nothing but the exclusive NOR gate. Now you can try that if you place different combinations of A and B, accordingly the output will be matching with the given truth table. This you can do at your own. I'm leaving it to you. But yes, so if someone asks you how exclusive NOR gate can be obtained from basic gates like AND gate and NOT gate, you can show up this expression to get exclusive NOR gate. Well, now let us come to very interesting aspect of exclusive OR gates and discuss their very interesting application, which is the application of exclusive OR gates as parity checkers. So before we talk about parity checkers, we first should know what is parity. What is the parity of a binary number? So actually, parity of a binary number is nothing, or binary data in general. It's not, binary data need not necessarily represent a number, isn't it? So it can be any data. For example, it can be audio, sound, it can be a video, it can be a photograph. So binary data in general, I think, is the better term. So if you have binary data, then parity of that binary data means number of binary ones in that binary number. So how many ones are there in that binary data? That represents the parity. So what are the possible options? Actually, the number of ones in a binary number can be either even or odd. Either the numbers are 0 or 1 or 2 or 3 or 4. Number of ones can be anything, right? So depending upon if that total number of ones in binary data is even, then we call the parity of that binary data is even. And if number of binary ones in that binary data are odd, then we will call that parity of that particular binary data is odd. Okay. That I already told you, even parity. Now let us try to see one example. So if you see this number, so what is the parity of this number? We can count here. How many ones are there? 1, 2, 3, 4, 5, 6. So in this binary data, we have 6 ones. So what will be the parity of this number? Which is even, because 6 is an even number. I hope it is clear to you. Huh? Similarly, odd parity means if the number of binary bits being 1 is odd, then we call that parity of that binary data is odd. For example, this number. Now you can count how many ones are there. 1, 2, 3, 4, 5, 6, 7. So there are total 7 ones or 7 highs. We will call the parity of this particular binary data or binary number is odd. So there are only two options for parity of a number. Either it is even or it is odd. Okay. Well, then what is the use of this parity? Why we actually need to bother about this parity? So parity bit is usually used in communication of binary data rather than saying binary numbers. And why does that help? Basically, we can track that in communication system, what happens, you generate a data at one point, then that data is transferred from one point to another point. And then at other point, we have a receiver which receives the binary data and then processes the information. But then during transmission, there is a possibility that because of many parameters which are beyond our control, there may be some thermal fluctuations in binary data, which is, say, suppose in binary data, one of the bit gets reversed because of those thermal fluctuations. Suppose any one goes to 0, then the whole meaning of the data changes. So this kind of risk of bit flipping is very prominent in case of digital communication. So to avoid that bit flip and to cross check if the data is correctly received as it was transmitted, we make use of parity bits. So how does that work? Suppose we have binary data which we have to transmit. Suppose this bits represents the data bits. So suppose this portion of the number or data represents the actual data bits which we have to transfer. This may be some image, means binary data corresponding to an image. This may be data corresponding to an audio. This may be data corresponding to some number. This may be data for anything, right? So these, you fix some bits in the binary data, and those are called the data bits. And we fix additional bit to the left of that binary data, and we call that bit as parity bit. So in this present example, you should note one thing, that this parity bit does not mean parity of the data bits. If you check these data bits, what is their parity? Okay, there is one more thing. Even parity is written with the number 0. Odd parity, we can say, okay, it is written with 1. Okay. So now what is the number of ones here? 1, 2, 3, 4. So total number of ones is 4. But still our parity bit is 1. So that doesn't mean that this bit tells you the parity of this number. No. But what is the parity, or how is this parity bit fixed? That's where is the idea. Whenever sending the digital data from source to a receiver, or from a transmitter to a receiver, we fix the data packets, the parity of the data packets. Whatever is your binary data, we fix its parity either to be even, or we fix its parity either to be odd. How do we do that? We do that with the help of this parity bit. So suppose this is a data. Now 1, 2, 3, 4, 5, 6, 7, 8-bit data it is. So what is the parity of this data? 1, 2, 3, 4, 5. What is the parity of this data? Even or odd? What is the parity of this data? Odd parity. Now what we have, suppose we are following a system where all the packets to be transmitted from the transmitter have even parity. So this data is not fit for transmission. That is why to this we add a parity bit, so as to make the overall parity of your data packet even. So what we have to do for this? We have to place a parity bit which is 1. Now this parity bit will make sure that overall parity of this data packet is even. So whatever is the data, parity bit makes sure that the overall parity of the data packet is even. Is this clear? Is this okay? Any confusion or question over this? Well, if there is no question, now let us take another example. This is another data. What should be the parity bit for this? Under the condition that we have to maintain the parity of the data packet to be even. So what should be the parity bit? What parity bit we should fix? 0. Correct. The parity bit for this should be 0, because the data itself has even parity. So our parity bit has to be 0, because overall objective or goal is to maintain the parity of the overall packet to be even, so that whenever we send a data packet from here, and we tell the receiver that okay, I am following, or I am sending you all the data packets which have even parity. Well, so he will check that at his end, is he getting the data with the parity, with the even parity? That is where we apply parity checkers and parity generator as well. So we will be in coming slide discussing about parity generators. First, we are trying to understand the meaning of the parity and how to place the parity bit. Let me give you another example. So this is the data. What should be the parity bit in this case? What should be the parity bit in this case? 0. Is it? Yes. Because overall parity has to be maintained even. The data itself has a even parity, so parity bit will be 0. Okay, let us do another example. What should be the parity bit for this data? Very good, very smart. This should be 1. So now you will see that all the packets, all the data packets on this side have even parity. So whatever is your data, whatever is the form of your data, you can always choose parity bit accordingly, so as to make the overall parity of the data packet to be even. Similarly, we can also choose odd parity system, where now this is your number, right? What should be the parity bit for this? In order to make sure that the whole packet has odd parity, what should be the parity bit? Very smart, very good. And what should be the parity in this case? Correct. What should be the parity in this case? Oh, do you think it is 1? Correct. What should be the parity for this case? Do with patience. I mean, don't be in a hurry. Correct. So that's how we can fix the parity bits to make sure that our data is either having even parity or our data is having odd parity. So that is what is the usage of parity bit. Now let us try to see in terms of hardware, or we can say the digital circuit, how we can generate and check parity. So let us now discuss here an even parity generator and checker. So the upper circuit here is showing a even parity generator. How this works, and what is the data size? It is 4-bit. So your data size is 4-bit, and the transmission data packet is 5-bit, because 4 bits corresponds to data, 5th bit is the parity bit. So this is an even parity generator. How? You can check with the, this is a 4-bit exclusive OR gate. I hope you remember what was the operation of exclusive OR gate. If number of ones at the input of an exclusive OR gate is odd, then what will be the output? Output will be 1. And if number of ones at input of exclusive OR gate is even, the output will be 0. I hope you are understanding what I am saying. So that is how this final combination will give you overall even parity data packet. Why? If number of or if the parity of these 4 data bits is even, the parity of 4 data bits is even, means number of ones in this data is even. Then what will be the output here? Okay, let me ask you, what will be the output here? Output will be 0, correct? So means, what does this combo do? Make sure that parity is even, because in that case parity bit will be 0. But if number of ones here is odd, what will happen? The parity bit will become 1, so that overall number of bits here in the output will be remaining odd, even. And that is what we call parity generator. Okay. Now suppose at transmitter end we have a even parity generator, then that this data travel through a channel. For example, in case of our mobile communication or online digital communication, what we are doing, I am speaking something here, that voice is being transformed to digital data with the help of some analog to digital converter and some softwares. Then that digital data is being transmitted to your mobiles with the help of electromagnetic radiations, isn't it? Your whole mobile spectrum is a part of electromagnetic spectrum, correct? So this data which I am talking here is first being converted to digital form, then it is being transmitted to a channel, then channel makes sure that the data reaches to the receiver, then receiver receives the data, and then that data is converted back to the desirable form. Because I am speaking here, you are hearing my voice directly. So means the data which is being transmitted is further than converted back to the desired form. But if during the transmission, suppose there is some bit fluctuation, means suppose your data had say 5 bits, and one of the bit gets fluctuated because of errors which may occur because of many unknown factors. So what will happen? At the transmitter, we are making sure that the parity of the data packets is even. So if one of the bits fluctuate, this parity checker at receiver end will do what? It will check the parity. So how does parity checker work? It is exactly the same operation, almost same, I mean. So you have 4 input exclusive OR gate, where we feed in the data which is received from the channel at receiver, and then we had also generated a parity bit, correct? So that parity bit is also fed to the input of this parity checker. Now what will happen? Your data had some form, right? So every 0 should have remained 0, every 1 should have remained 1, correct? So if that is the case, suppose our data had odd number of ones originally. Suppose here we had transmitted odd number of ones. Then again, if there is no error in between, the number of ones will remain same, odd. So what will be the output here? Output here will be 1, right? And in that case, because we were following even parity generator, so number of ones was odd. So what should have been the parity bit? That should have been 1. So this is 1. So 1 being fed here, 1 coming out here. In an exclusive OR gate, when both are 1, what is the output? 0. So if the output is 0, means no error. But anyhow, if any one of the bit gets changed due to any reason, what will happen? The parity will change here, output will change here. Parity bit was carrying something, but then there will be a change because of one bit only, and then that is how what will be the output here is 1, and this is what will mark a error message that your data is faulty, so that you can make sure that data is retransmitted or it is fixed properly. Then is odd parity generator. Is this even parity generator and even parity checker clear to you, or any confusion or question over this? Is there any question on this part? Okay, means it is clear. Now, we discussed that it is possible to follow either even parity scheme or odd parity scheme. So there is no preference that, okay, any particular parity is preferred over other. But yes, you have to follow a specific parity. So if we have to go to odd parity generator and checker, the same circuit, if it is deployed with the help of a NOT gate, then that will become a odd parity generator. The operation is also straightforward. I'm sure you can understand what I mean by putting up a NOT gate here. So that in this case now, this bit will accordingly be reversed. And this will make overall transmitted data to have odd parity. Similarly, you will have a odd parity checker, same idea. And that is how we can employ either even parity or odd parity system. Well, now that was a simple case. Means we had a data which is 4-bit, and then fifth bit was used for parity. Then you may ask, okay, what if the data is containing many bits? So you can actually employ n input exclusive OR gate, and you know how to get that n input exclusive OR gate. We have seen it in the previous slides. Maybe let me take you to the beginning, right? So that is how we can, this is the circuit here. This is how you can get any n input exclusive OR gate. So then, I mean, that is how we can employ that for any n bit data system. So, I mean, what is the bit size of your communication? That's important. So this is representing a 8-bit odd parity generator. Why odd parity generator? You can check actually. You have 8 data bits. What is the situation here? There is a NOT gate placed here. Make sure the operation is not wrong. Huh? I mean, you cross check. Yeah, even parity generator, we didn't have a NOT gate. For odd parity generator, we have a gate here, NOT gate here. So if you want a even parity generator, you remove this NOT gate. That's it. So that is how we can get higher bit parity generator and even checker. Now you can also take a parity checker, design a parity checker from this kind of circuit. They are very similar to each other. Well, is this okay, or any question up to this point? All right. So this completes our first unit, which contained basic logical gates, basic logic gates, and then their small applications and their truth table, how we can design those logic gates from fundamental gates or universal gates. So these are the symbols. This is a quick summary: AND gate, NAND gate, OR gate, NOR gate, exclusive OR gate, exclusive NOR gate. This is called a buffer. If there is nothing like a not, there is no dot here, this is called buffer. So what is the role of a buffer? It keeps high voltage high and low voltage low, but it supplies high current, because to drive the gates, we require some non-zero value of current. So if we withdraw too much of current from our circuit or from our gate, the voltage may fall, because V is equal to IR, right? So if current is large, voltage drop across the various components of the circuit will increase, which may at some points lead to drop in the output voltages, which may lead to 1 going to 0, right? As the voltage will drop, 1 means high voltage, 0 means low voltage. So there may be misinterpretation of data. So to avoid this, I mean, when we have large number of gates which have to be driven from a particular IC or from a particular gate, then we use current buffers there. Fine. And then this is called nothing but a inverting buffer, like a NOT gate, nothing very different. Well, so that's all for today. If there are any questions, I will be happy to answer your queries. And well, thank you very much, and take care of yourself. Are there any questions? Oh, attendance. Very good, very smart. Is there any question? All of you sign your attendance. That's okay. Um, if there are any questions, please ask me or let me know so that I can help you. Okay. Should doesn't have any question. Anyone else having a question or confusion? Well, if there are no questions, I thank you once again. Hope you will have a nice weekend. Take care of yourself. We will be meeting in the next class. Till then, goodbye.